Hydrogen peroxide is finding new uses as an oxygen source for the treatment of municipal water and industrial wastewater. The balanced chemical equation is 2 hydrogen peroxides will produce 2 waters and 1 oxygen. We're going to calculate the volume of oxygen at 23 degrees Celsius and 726 millimeters of mercury that could be liberated from 1 liter of water solution, which contains 30% hydrogen peroxide by mass. The density of this aqueous solution is 1.11 grams per cubic centimeter, or grams per milliliter. Keep that in mind. Eventually, we will make use of the ideal gas law. We're going to write the linear equation as PV equals nRT. I'm not a big fan of having R memorized. I'd rather customize it as necessary. So eventually we'll end up with moles times temperature divided by P times our customized R value. Now when we get started, we cannot start with our 30%. We cannot start with our density. And the reason for this is concentrations are conversions. And densities are conversions because they allow us to move between mass and volume. We're going to start with 1 liter of solution. I'm going to go ahead and convert liters into cubic centimeters. And the reason that I'm going to do this is the next step is to go to density. The concentration of the hydrogen peroxide is by mass, a percent by mass. So, when I look at my ideal gas law, I know I need to get to N somehow, some way. There are 1,000 cubic centimeters, or milliliters, in every 1 liter. This allows me to get on track with my density. And so we're going to use the 1.11 grams of solution for every 1 cubic centimeter to get rid of those cubic centimeters. Once I'm into grams, you need to remember that it is of the solution. 30% of that solution, or 30 grams out of every 100 grams of solution, are going to be hydrogen peroxide. If you'd prefer to write these as percentages rather than grams, you can. I'm going to go ahead and write them as grams. You'll notice grams of solution is now gone, grams of hydrogen peroxide is left, and now I can use my molar mass of hydrogen peroxide to determine how many moles of hydrogen peroxide are there. After that, I'll use the balanced chemical equation to determine how many moles of oxygen would be liberated. When I look at the balanced chemical equation, I see that for every 2 hydrogen peroxides, 1 oxygen would be liberated. I can write this scaled up as 2 moles of hydrogen peroxide for every 1 mole of oxygen. All of this was to get my N. It takes up a large amount of space, but slowly but surely I can move from liters of solution to moles of my gas. After that, I already have my formula set up for the ideal gas law. I just need to plug in temperature, which remember we need to add 273.15 to get it into Kelvin, put in my pressure, and after that customize an R value that allows me to cancel out moles, Kelvin, millimeters of mercury, and leave me with a volume, so I'll know how much volume of oxygen there is. Remember, my customized value is coming from the idea of 1 mole of any gas under ideal conditions taking up 22.4 liters of space at standard temperature and pressure, or STP. Standard temperature is 273.15 Kelvin, and standard pressure is 1 atmosphere or equivalent. Since they use millimeters of mercury, I will too. Again, this is a customized R, and most people can find these values on a mole bridge. I like it because it allows me to cancel out units and leave me exactly with what unit I'd like. Once I know everything's in place, we multiply across the top, divide by the product of the bottom, and solve. This gives me 124 liters of oxygen gas. This is the V1 that I was looking for. My second set of conditions was in R.